start the sharing of my iPad. Okay, good. So I think everybody's seeing my screen now. Okay, so today what we're going to do is introduce and talk about some features of QCD. Okay, so we're not going to do a hugely in-depth look into QCD. QCD and the physics related to how colored objects interact with one another, and especially the physics of how QCD works at low energies and makes bound nuclear systems, is a course that can take, you know, that could be an entire course unto itself. So that's a very active area of research. We're going to hit some of the key features and talk about some of the important questions and main features here. But again, if somebody is really interested in some of the this might be an interesting place for one of you to pick up on with your student presentations or presentations at the end of the semester to sort of probe what are some of the outstanding questions in modern work happening in understanding low energy QCD. So what is QCD, first of all? QCD stands for quantum chromodynamics. Okay. So this is in, right, it looks similar to QED, which we've studied, which was quantum electrodynamics. So that was the study of objects that are charged interacting with one another. This is the study of objects that are colored interacting with one another, right? So you've probably heard this term colored objects, or right, quarks carry color. It's just a funny name, right, for a different type of quantum mechanical property that objects can carry with them, right? So you can think of it like a type of charge, right? A property that we observe in nature that helps us identify these different things. And we're going to see that the experimental evidence shows that there's 3 types of these things, and so people, right, pick this term color to represent the type of charge. So some people will call it color charge because it's essentially acting like the charge in this theory. It just gets labeled instead of plus minus as red, blue, and green. And right, so the other reason people like using this color terminology is that to describe a neutral object in this theory, just like for charged objects, right? If you want to build a neutral object out of charged objects, you got to bring two, right, a plus and a minus together, and they'll cancel each other out and leave you with a neutral object. In this theory, to get a neutral object, you need one of each color, red, green, and blue. And so the idea is that red, green, and blue would give you like a quote unquote white object, right? And then so some people might call it a white object, but that just means it's color neutral. Okay, so we're going to have some of these terms. Okay, so what we're going to try to do to start today is essentially we have all the tools that we need to describe right, the machinery to try to understand these interactions. And we could go through the same treatments. We could assign different charges with different structures and try to tease out what the Feynman rules have to look like using perturbation theory. And so instead of repeating that, which just looks identical to what we did in QED with this new property, we're going to start just by writing down the Feynman rules, and then we're going to focus on some of those different rules and highlight where they're different from QED, why they're different from QED, and how that leads to different kinds of physics. Okay, so what are the ingredients of quantum chromodynamics? Well, first thing, just like we needed in QED, we need particles. Okay, and those particles are going to be able to, right, are going to be able to interact with each other via, right, virtual, let's say they're going to be able to act. So we need some sort of particles, and we need some sort of, right, some sort of vector bosons, right? We need the analog of the photon in this theory, okay? Okay. What are the particles? The particles in this theory are going to be the quarks. So we find in nature a set of particles that have this extra quantum observable, or this extra property that we call color, and these objects we call the quarks. And we've written down that there are 6 quarks that we've observed in nature, the up and the down that we've talked about before, that form this isosymmetry pair that we're really familiar with, because these are the things that build up most of the protons and neutrons in the nuclear states that we're familiar with. But there are heavier versions, the charm and the strange, and the top and the bottom as well. And then what is the vector boson that we're going to have in this theory? This is this object that we call the gluon. And so there's one gluon, and these things, right? What are some properties of the gluons here? This is a spin 1 boson. And the quarks are fermions. And they're spin 1/2 objects. Okay. So this is what we're looking at. So that's all well and good. So that looks similar to what we had for QED. So how are we going to describe? Let's focus on the particle states. How are we going to describe the particle states in this theory? Well, they are still spin 1/2 fermions, so they're still going to be described in terms of their spin states. So we're going to describe them in terms of Dirac spinners. These are the same spinor objects that we've been looking at for, the last several chapters in the book, right? Our U's and our V's that describe the spin states of these fermions. But then there's an extra piece we're going to tack on in this theory, color states. Okay. And what do the color states look like? These color states, right, we're going to just represent them in this vector form here, where, for instance, I could have one that I'm going to write down like 1, 0, 0, right? And this represents, right, the color charge of this thing. So I have a little vector here that's going to represent whether or not I have a red, green, or a blue object, something like this. Okay. So for instance, a state could be something like, right, a good particle state to work on in QCD would be something like U3 1 0 0 would be like the way I could represent a state in this theory. It's a spinner, right? It's our U3 Dirac spinner, and then it has this particular color state, right? It's a red, right? Or we could say, right, the shorthand for this would be like a U3 particle that's colored red. Okay, there's a few different notations that you could use here. But we're going to use the, this vector notation because we're going to build a set of new, right? You can imagine then that there's going to be operations in this theory that act on those color states and do interesting things, right? So there's going to be interactions that play with the color states. Okay, and we'll see what those look like here in a second. Okay. What does a typical interaction in QCD look like? Well, just like we saw before, the fundamental interaction in QED was the lepton, right, the charged lepton coupling to the photon. We could write down a similar diagram, draw a similar piece of a Feynman diagram in this theory, right? We could have our quark, say, and it's going to emit a gluon, something like this. Okay. But here's one major difference coming now between the theory for QED and the theory for QCD. Remember, for the photon was a neutral object, okay? But in this theory, the gluons, they carry color with them. Oops, carry color, okay? And how do they carry color? Well, they have to carry it in a specific way because we can see on this diagram that the two quarks here are, right, they're colored objects as well. They have to have some color representation. So say I had something that's like the most straightforward kind of scattering you could think of. I have a red scattering off this way, and I end up with a red quark in the final state, something like this. Well, what's the color then that the gluon has to carry away? Well, the color we're thinking about like charge. So the color has to be conserved through this interaction. Okay. And so either this thing could be, right, so we have to write this as neutral. So how could we write this as a neutral process and still put color labels on it? Well, we could write it something like red bar. So it's some mixture of red and anti-red. So the gluon actually is getting labeled by two different color states, right? A red and an anti-red. So that's not very different still than a photon, because a photon we could technically have labeled it as a plus minus state, and it's just some neutral object, and it's not very interesting, right? But the rub comes in if we have a different quark scattering here. Say I start with a red quark. What I can do is I can end up, right, my interaction with my gluon can change the color of my quark. So I can end up with a blue quark over here. Okay. This was something that we don't see in QED, right? The photon can't change the charge of my lepton through that interaction. So what is the charge that gluon has to carry with it? Well, the total color has to be conserved as I go through here, right? So the labels, the color labels on this gluon has to be red. Something has to carry that initial red index through this interaction, right? I need to still have red on the, say, the right-hand side of this diagram. And I have blue here. Well, I didn't have blue in my particle to start, so this has to be an anti-blue, right? So again, I have to label it by two color labels. This is a red. This has to be a red anti-blue gluon. Okay. And so, I can make, yeah, go ahead.
Are gluons always two colored?
Yeah, so gluons are always two colored objects. Right? In our theory, that's the way they write. So I can write down then a set of gluon states. Okay. And the gluon states look like, right, all of the different possible color combinations that I could get for that, for the gluons, right? So what does that mean? I can have something that's like a red and a blue, a red and an anti-blue, right? Something like this. But it turns out that if you're careful about the way you have to be careful about the way you write down these states, because again, they're different, right? So we know that I have different states represented by that matrix, so red, green, and blue. And if I have two of these things together, I can make different combinations of them, just like you would with some spin algebra. And so I need to be careful about making a set of states that are orthonormal with one another. And if you're careful about that, there's different ways to do this, but the most common representation is what I'm about to write down. So there's let me just write them down. Red, blue bar, minus blue, red bar. Okay. So I can write down this set of states. So I have eight set of states here. So there's some octet of states that I can form here. And I can also write down a singlet state that is just red, red bar plus blue, the thing you might expect, red, red bar, blue, blue bar, plus green, green bar, with some normalization factor here. Okay. So what are these states, right? This is essentially, so first of all, the boson, or the gluons have to still be bosons, so they have to obey boson statistics. And I need a set of color states that are, that span this whole space, this whole color space that the gluons are allowed to occupy and are complete, right? So I need a complete set of states to span this thing. So this gives me a set of orthonormal states that span this space and have the right kind of symmetries that I need for, you know, boson statistics to still hold. Okay. I think one of the homework assignments, if I remember right, is playing around a little bit with these different states and convincing yourselves they have these properties that we would want when we write them in this way. Okay, so you'll get to play with that. So the point is, like, in general, we tend to write R, like in a little simple sketch, we would write RB, but it's a little, right, if we want things to be one of these gluons to be really one of these fundamental states in this representation that I have over here, we would have to pick one of the colored states that I've represented on the right-hand side. Okay. So, okay. What else about the gluons? The gluons in this theory are also massless particles, just like the photon. Okay, so they don't carry mass with them. We're going to see that when we get into the weak interaction, that doesn't always have to be the case with these vector bosons. The weak particles have a huge mass associated with them. But in this theory, we find that a massless gluon does the trick of explaining the data that we see. Okay. And how is it going to be represented? The gluon, right? So a real gluon is represented by a polarization state. Okay, that we can call epsilon. Some polarization vector epsilon. Okay, same thing we saw, very similar to, right? Remember when we had a real photon being emitted in our processes, we represented them by one of these photon polarization states. And so the same thing happens with the gluon, right? The gluon has, it's a spin 1 particle, and it can have that spin aligned in a certain way along with its momentum. Okay. So the next thing, so we see that in this theory, we have that the gluons are colored objects. And this is what makes all the difference between QCD and QED, right? As soon as you say that the gluon carries the charge of this theory with it, color charge with it, well, now you have the possibility for the gluons to self-interact. Okay, so that wasn't a possibility in QED, right? Why? Because I have a photon cruising around. It's a neutral particle. It doesn't do this thing where it generates its own field and makes another photon. Like, the photons just cruise along and they don't interact because they're neutral objects. But here I've got the gluon, and so that it's colored, and so it turns out that I can have interactions like the gluon coupling to, having a vertex and coupling to two other gluons. Okay. So what is this? This is like gluon emission. I can basically have a gluon cruising along and emit off, right, radiate off another gluon from it. Okay. And I can even have a process like this, where I have a vertex that has, okay, that has two gluons, right? It's a vertex that has four arms coming out of it, right? So I can have a coupling like this. And this is due to the, right, due to gluon charge. And these are the only two kind of couplings diagrams I can draw for the coupling of the gluons. And why is that? That's because still, right, if I want to conserve charge through this theory, right? So you imagine that I start with, I could write this down. I start with something that's red, green bar over here, right? I would have to be able to find the states of the gluons on the other side, right, that would do this thing. So maybe this guy is, I don't know, a red blue bar, right? This guy would have to be like a blue, what would this have to be? A blue green bar, right? I can have something like that. I can find a set of color states that conserve charge through this property. And you can also find, it turns out, if you find the right combinations, you can find a set of color states that'll conserve the color charge through this type of interaction as well. Okay. But if you start to add in, right, a fifth gluon into this vertex here, you'll no longer be able to find combinations of gluon states that'll conserve charge through that vertex. Okay. So I have these, right? And so now this is immediately a large deviation from what was happening in QED. The fact that the boson, right, the vector boson in this theory can self-interact is a huge difference. Okay. And we're going to come back later in the class to why that's an important difference. But this is where all the difference in the world comes from. Okay. All right. What else do we need in this theory? Well, it turns out we're going to need some matrices to, right, we're basically going to need we're going to need color interaction matrices. Right. You can see we wrote down this set of, we said that the objects in this theory carry these specific color states. And so we're going to need some, right, just like, so we're thinking about the color states, however you want, right, is akin to something like the spin states for a normal particle, right? There's two different projections for spin, and I can label particles differently that way. Well, now I have three possible colors. And for the spin states, right, we had the spin operators, we had the Pauli matrices in the lowest order representation of that theory for how, how I could act on a particle and probe. I could try to measure the spin of the particle, or I could have it interact with a magnetic field. So I need the same idea in this color theory. And it turns out there's a common representation that people use in this theory that's represented by the Gelman matrices, the Gelman lambda matrices. Okay. And there are 8 of these matrices, and they look something like this. So lambda 1 looks like, as you might guess, they're going to be 3 by 3 matrices to act on these 3 component color state objects. 0, 0, 1, 0, 0, and sorry, I put a 1 in the wrong place. Let me find my eraser. Okay. Lambda 2 is like 0, I, 0. Okay. And then so on and so on. So lambda 2, lambda 3. I'm going to start writing these down a little bit more quickly. Looks something like this, and then zeros everywhere else. Lambda 4 looks like 1, 1, and then zeros everywhere else. Lambda 5 lambda 6. All right. So these dots just represent zeros right now, just for sake of writing these quickly. And lambda 8. Oops, I started doing subscripts there. Looks like 1, 1, minus 2. Okay. All right, so I have these different matrices, and you can sort of see what these would do, right? Somehow there's a set of these matrices that mix, right? Mix the states together, can transform from one color object into another one, transform the color state. So that might be something that's important at this vertex where I'm changing, right? Changing the color of one of my quark objects through the vertex to another color. And then there are these ones that, right, maintain the color constant, right? These are the guys that are going to be related to that singlet state where I don't change color through my interaction vertex. And these matrices are written down in this specific way because they obey an interesting relationship. If I write down their commutator, there's a rule that looks something like this. 2i, and then there's this thing that we're going to call f that has labels like alpha, alpha, beta, gamma, lambda, gamma. Okay, where this f thing here, f 1, 2, 3 is equal to 1, f 4, 5, 4, 5, 8, and f 6, 7, 8 are equal to square root of 3 over 2, and the rest are all equal to 1/2. So there's a special rule there that I get for the relationship between these matrices. Okay. So with all those tools, then we can write down the Feynman rules for QCD. So let's see what it looks like. So the Feynman rules for QCD look something like this. External lines, right? These are the real particles. Okay. What do they look like? Well, I can have the quark state, right? And I'm going to represent it by a line in my Feynman diagram. And it looks, right, it has a spinor state associated, Dirac spinor state associated with it, and one of my color state objects. And I can have an antiparticle, right? If I have something that's cruising like this, say I have an antiparticle cruising along something like this, I can have my U bar S. Right, again, it's represented by a Dirac spinor and some color state like this. Okay, so these are the quarks. These are objects that we call quarks, right? So this is the definition of a quark. A quark is a spinor state that has one of these, right, that has a color representation as well. And then I can also have gluons, right? So I can have real gluons that are radiated on shell gluons. In this theory, a gluon is represented as a little squiggly spring-looking line in our Feynman diagrams. Okay. They have these polarization states, epsilon, and they carry some 4 momentum with them. And then, right, they also have some state that we're going to write down as A. And this thing associated with it is, right, so it has some label, right? So this is one of the color states for the gluon. So again, they have these 2 color labels, and we are going to hide that in these objects. They're one of those things that we wrote down at the top, right, in that long list of 8 different states.
What is that subscript on the epsilon?
That's a mu. Sorry. I don't know if that was any better. It's just a polarization state, right? I mean, it's just a label that basically is going to tell me what, remember, what were these like for the photon? The polarization states, I could basically have the spin of the photon pointing along the direction of the momentum or against the direction of the momentum. And I have the same thing here because I have a spin 1 object, and so its spin projections can be aligned or anti-aligned to the direction of the momentum. And so that, whatever that scribble I wrote there, it's just an index that tells you which one of those polarization states I'm in. Okay. All right, so those are my external lines. So we have ways to describe these states. Now I need to be able to write down the rules for my propagators, right? So this is 1, this is the states. 2, we know we're going to need propagators. Right, or virtual, right? Things that describe the virtual particles in our theory. Right, these are the objects that we don't really expect to observe in nature, but that transfer momentum across different legs of the diagrams, right? Across the different current parts of the diagrams. And how do these look? Okay, well, what can we have? There's 2 different types of propagators we can have in this theory. Again, we could have a quark acting as a propagator. Okay, what might that look like? Why would we need a quark propagator, right? We might have, say, a gluon coming in here, interacting with a quark, and that quark scatters off like this, radiates a gluon like that, and creates another quark, right? I could draw a diagram like this, and I would need a quark propagator, right? This quark state in here is a virtual particle that's transferring the momentum through to those final state particles. What does the propagator for this quark look like? Well, it just looks something like I over, right? So there's going to be some momentum transfer, some four momentum associated with that virtual particle that we usually call Q. So this carries, say, Q. It's going to look like I Q slash plus MC, the mass of the quark, divided by 2Q minus the mass of the quark, MC squared. Okay. It looks just the same as the quark, as the propagator term that we saw for, say, an electron when it was acting as right, and it was acting like that, right? Or the muon, right? We saw diagrams where the muon could be this intermediate virtual state that we had, right? So it really looks just the same here. And the gluon, right? I can also have gluon propagators, right? So this is a quark propagator. What does the gluon propagator look like? Well, gluons. Let's convince ourselves we need a gluon propagator. So what would an interaction look like where I have an intermediate gluon state? Well, a simple one to draw would be I have a quark and an antiquark coming together. Oops. annihilating and giving me a gluon, and then that gluon field decays back into, say, a quark and an antiquark, right? It could have a process like this that would require a gluon to mediate this process. What do these terms look like here? They look like this. The gluon that's going to be propagating in this theory has some alpha, some color state associated with it, and it has this polarization state. Okay, it's also going to have some form momentum that I can assign to that propagator. And then on the other side, right, there's going to be some additional labels that I can make for how it's going to couple to the quark side. And I'm going to write it down something like this. It's going to be minus I g mu nu delta over q squared. Okay. Where those delta terms that you see there, right, are the g nu mu are the g factors we've seen before. The delta terms are built from these Gelman matrices in a specific way that we're going to write down a little bit. But essentially, there's a set of, right, there's a tensor term that we have to write down, and we'll define that here in a little bit. Okay. What else do we need? So we have the particle states, we have the propagator rules. What's the last one we need? We need the vertex rules. Okay. Now, in QCD, it's a little more involved because we have 3 different type of vertices that we can write down, right? In QED, there was one and only one vertex, right? The charged particle coupling to the photon. Now we have 3 different vertices that we can write down, right? We can have the one where I have my quarks coupling to the gluon, that this is what looks like what we saw in QCD. And what's the Feynman rule for this thing? Well, it's something like you might expect. It has a term that looks like IGS, right? Where GS is somehow the coupling strength here, right? This is somehow related. This is somehow proportional to alpha, or the coupling constant in my theory. Right? We wrote that as GE for QED, right? It just had a different coupling constant here. So this in principle has the same form, but that coupling can be different from QED, so we give it a different label. There's a factor of 2. And then we need one of these Gelman matrices. Okay. And what else do we need? So we need a Gelman matrix here because the quarks in principle can change color through this interaction. So that's a different thing than can happen in QCD, or sorry, QED. So we need those things. And then also I need a gamma mu term, right? This is still a vector interaction, right? Remember we had, so what did this look like for QED? For QED, this looked exactly the same, except for we
lost the screen share.
You lost the screen share.
Thanks. Or at least I did.
Yeah, I did too.
Let me try it again. Let's see if we're back. Are we back?
Yep.
Okay. So this looks just like we saw for QED, except for this term, right? So this guy is the new term. Remember in QED, this vertex term looked like minus IGE over 2, and then there was the gamma term, this vector coupling term, because I have a spin, right, 2 spin object coupling. So now I have this extra term, right? This bit is handling, right, the spin couplings, basically the spin nature, and this guy is handling the color piece of the coupling. Okay. But now there are additional states that I have to write down. And these are ones that we we're not allowed in QED. I can have
Dr.
the
Mitchell, what was the
three
G?
gluons coupling to one another, right? I can have this thing. And when I have this thing, I can write down a Feynman rule. Now there's a bunch of labels I have to write down on this thing because each of these gluons carries some polarization state and some color state with it. And so I'm going to label both of those numbers, quantum numbers here. So the first number is, say, the color state, and the second one is the polarization state of this gluon. And here maybe I'll do a gamma and a lambda. And each of them carries now some 4 momentum with them. So say K2, K1, right, and K3, and I need 4 momentum to be conserved through this vertex still. And right, people have worked through this, right? I mean, you can imagine that it becomes fairly involved to make sure that 4 momentum is conserved through this process and all of the various conserved quantities end up right. But when I do that, what you end up is that there's a coupling rule for this, the vertex, right? So we're writing down here, the vertex term has to look something like minus GS. Again, it has to depend on the coupling strength in this theory. There's a term that's related to this F expression that we wrote down earlier. And right, then there are these G terms that couple together the polarization states. So K1 minus K2 lambda. And I have to have all of these G matrices to couple all of the different polarization states in the proper way. Remember, the G matrices before were made from the gamma matrices, right? So somehow these are tensored quantities that are built from the gamma matrices that handle the spin properties through the vertex. And K2 minus K3 new, and then I need one more. Okay, something like this. Okay. So, I mean, it's right. I mean, it's a fairly complicated coupling to have these 3 gluons. Why? Because now I have, why do I need this complicated structure? Because now I have these 3 objects, and each of those 3 objects is carrying one of these like dual color states with them, and they have these polarization states. So this vertex has to handle, right, all of the combinatorics, all of the interactions of those 2 color states getting swapped around in the proper way through this vertex, and also for all the spin properties to be transmitted through this interaction. And the net result is that you end up with an expression like this. Okay. When you have a vertex like this, it's convention that the 4 momentum vectors, the 4 momentum points into the center of the vertex when you draw it like this, when you write it like this. Okay. And if you want the momentum to point outwards, you just switch the sign in the equation, right? If I had the gluon needing to carry the momentum in the opposite direction, I just have to put a minus sign in the vertex rule that we wrote down to. Okay. And we have one more type of vertex term that we can write down in QCD, because I can have 4 gluons all interacting together at a vertex. Okay. And right, so now I have 4 independent polarization and spin states, gluon spins or polarization and color states that I can write down. Oops. So each of these has a label that tells me something about their spin orientation and their color state. And again, I'm going to write down a convention where they're 4 momentum. They're each going to carry some momentum into the center of this interaction. And when I do this, I get a pretty messy looking thing, but we can still write it down. It looks something like this. It ends up that looks something like GS squared over, times. And now I'm going to build this up out of F and G matrices, things that we've defined already. And it looks something like this. Now I have to have two F matrices to handle all of the interesting possible color couplings through this object here. And then some spin coupling terms, something that tells me how the spin states are going to get happening. And there are actually, I'm not going to write them all down, but there are actually two other terms that look just like that first one, different combinations of F and G's to get all of the various permutations you need correctly. You can look them up in the Griffiths book to see the rest of them. Right? Notice here now, because I have 4 gluons and I have all these different indices here, that I have a lot more combinatorics, right? All these common vertices that I sum up here means I have to sum over all these possible states if they're, ambiguous at these different vertices, or if I don't, if the spins are independent, etc. And right, it looks something like the thing above, but squared, because now I have an extra gluon in the mix. And you can see that one thing to point out, an easy thing to look at, is that the strength of this vertex goes like G squared, right? And if G was a very small number, right, then it means that kind of 4-gluon coupling would be subdominant, and very frequently we wouldn't have to worry about it because it would be a rare event to have this kind of coupling, right? If GS was the same as GE, right? If the coupling was the same as the electromagnetic coupling, this term would be suppressed in a significant way compared to the vertex terms that are happening on the top diagram and the one above it that are at order GS. But since this is strong interaction, what people find experimentally is that GS, this coupling, right, is proportional to 1. It's not a small number. And so these kind of gluon couplings happen very frequently in nature and in this theory, right? This is actually just almost, it's basically as likely to have 4 gluons self-couple as it is to have 3 gluons self-couple like this in this theory. Okay. Okay. So that's great. Those are the Feynman rules. What the heck do we do with the Feynman rules? Well, we do the same thing, right? What do we do with all these rules? We do the same thing we do in QED. We calculate invariant scattering amplitudes with these Feynman rules, and then we calculate, say, cross sections or decay widths or interesting properties that we want to understand. Let's use these rules to write down the invariant scattering amplitude for a simple process. Okay, let's look at, say, U d bar scattering. Say U d bar goes to U d bar. Something like this. Okay. What does this look like? What does the Feynman diagram for this look like?
It would be just like our electron muon scattering, except with the gluon, right?
Yeah, this is just going to look like electron muon scattering, except for with a gluon in that state, right? So I would have something that would look like, say, a U on this side and a D bar on this side here. right? And then I would have a gluon mediating that exchange. Okay. Let's write down the invariant scattering amplitude for this process. What does it look like? Well, we're going to use the Feynman rules. The Feynman rules are, all we have to do is go up to those rules we just wrote down, find my propagator terms for each of the legs of these particles, right? So I should have, or sorry, not propagator terms, find my external line rules for the 4 quarks in this theory, because they're like real quarks that are on shell. And I'm going to have a gluon propagator, and I'm going to have these vertex terms here. And I just find those and I multiply all those together, right? That's what the Feynman rules tell us. So M, the invariant scattering amplitude, has to look something like this. It looks like I. And let's label this, right? So let's label these things. So this guy, say, I'll call particle 1. This guy we can call 2. This guy we'll call 3. And this guy we'll call 4, leg 4. Okay. So the first bit is, I would have something that's like this: U bar 3 C3 dagger minus I GS over 2 lambda alpha nu. Okay. U1, say C1. Okay. So here's the first bit. What is this? This is, say, that interaction in, right, this is the interaction that we see in that top part, right, where I have a particle scattering through. This is that current happening in this top diagram here. This is 1 scattering into 3. Okay. I've got the vertex term there, and I've sandwiched it between the 2 states, the initial state and the final state. And then I'm going to multiply that by, right, the state for that lower diagram here where I have the antiparticles. So I'm going to write it down in terms of my V spinor states like we've done before. So I have V2. It's got some color state associated with it. Oops, it's a dagger. And it's also a quark coupling to a gluon. So it has the vertex term. If we go to our Feynman rules, again, it should look like GS squared, or sorry, GS over 2. There's my color matrix. Oops, let me give it a different label. Let's not use alpha. We already used that. Beta, gamma nu, V4, C4. Okay. So that's the current happening on this lower leg here. And then in between, we have to write down our propagator term. And our propagator term for a gluon propagator looks like minus I G mu nu delta alpha beta over Q squared. Okay. Something like this. So it looks, right, this looks a whole lot like QED, right, for this diagram. I could try to mimic what I saw for QED, right? For QED, the potential for QED, right, had this form that was this dipole form, and I wrote it down, right? I could write it down. It looked something like alpha, say, E over H bar C over R, and then there was some factors that sat out in front of it, something like this. There was this dipole form, right, to the, sorry, there was this 1 over R potential for the electromagnetic interaction. Now we can see that this is really no different from a quark and an anti-quark coupling to one another, right? Instead of having alpha E here for this potential, this has just got to be some alpha S that's going to be the strength of the coupling for the quarks to the gluons here. Okay, so that's a simple example. And we could go through, and your book has lots of examples for building more complex diagrams, but essentially, now that we have the Feynman diagram, Feynman rules, any complex diagram that I write down, I just go grab all the appropriate pieces and write them out multiplicatively. And then the question is just grinding through all of that matrix algebra and all these indices and all the permutations, over all the possible combinations. And so, right, in principle, the rules are easy to write down. The calculations become complicated in this theory for two reasons. One, I have a lot more indices, right? I have more quantum degrees of freedom that I have to keep track of through all these interactions. And two, my perturbation theory is not working well anymore, because when we go look at these processes, we see that that coupling strength is really large. So perturbation theory starts failing us. Okay. Oh, sorry. So these what are these F things? These F things are just extra terms, factors that come from the couplings of color states. So this F term looks something like this. And if you calculate these F's, they end up being just numbers. And these numbers end up being minus a sixth for the octet state, and plus 4/3 for the singlet. Right, what is this? This is basically just doing, we know that gluon that gets radiated there can have these different colors associated with it. So there are all these different the ways that it can propagate that color through this interaction. There are multiple ways. And so if that gluon happens to come from one of those combinations that we wrote down in the octet state up above, that F terms ends up, if you do this calculation out, ends up being minus 1/6. And if it comes from that singlet state, it ends up being positive. It ends up being 4/3 here. And right, this is already something else interesting about QCD, that this color bit, right? Look at what happens with F here. F here, depending on the type of gluon I have, changes the sign of the potential. Can change the sign of the potential. And for QED, for QED, right, if I have an electron and a positron interacting with one another, right, in general we know that potential is going to be attractive, right, and so this potential would have this negative sign associated with it. But here you can see for most of the gluons that F term is negative, and it gives this interaction the opposite sign that you would expect between, right, but to the QED analog. Okay, so there's lots of funny bits about the way, even though I have a charge and a colored and an anti-colored quark scattering from one another, some of the times, depending on the way the gluon is radiated and the combinations of colors I get, some of the times that's some of the time that's an attractive interaction, some of the time it's a repulsive interaction. Okay. Oops. I lost the sharing again. Sorry guys, I'm having some bad internet today, I guess. So that's interesting. So the sign of the potential, just because we've introduced these color states, can be something that we don't expect, right? Or that is not following the same intuition we have for regular charged objects interacting with one another.
So I just noticed something that may be entirely coincidence, but the octet states, there are 8 of them, so if you were trying to sum over all of these states, you would end up with 8 of those in just the one singlet state. And 8 over 6 is 4 over thirds, but it's just negative. Is there something to that, or is that just a coincidence?
No, it probably comes from the counting. Yeah, it probably comes from the combinatorics. Yeah, I don't think that's a coincidence. Okay, so we've got about 10 minutes left. Let's talk about one other big difference in QCD, right? One other thing that this introducing this interesting color charge, right? So the big difference, right? In principle, we've made a small change in this theory, right? The small change that we had is that there are 3 different kinds of charges, right? And that the boson in this theory can itself carry charge, can itself carry charges, the charge signs with it, right? These dual charges. Doesn't seem like a major change, but there are giant implications to doing that. The first one we saw is that that means the gluons can self-couple. And we can talk then about an idea or a concept in this theory called asymptotic freedom. Asymptotic freedom. I'm not sure I spelled that right. I don't know why I'm having a weird moment where that doesn't look like a word. Maybe I've got it spelled wrong. Right? And what does this mean, that asymptotic freedom? Well, we know that, right, we just said that, alpha E, the coupling in the electromagnetic theory, is this thing that's like 1 over 137, right? It's this small coupling. And alpha S is like order 1. So that's a big difference here. But we could ask ourselves, how does alpha effective in, say, epsilon? So let's think back to QED. How does this vary with, say, the 4 momentum exchanged in some process with say Q squared? Okay, this invariant 4 momentum property. And what do I mean by this? So in QED, we could write this down, right? I had a charged particle, say electrons scattering from muons, and I could exchange a photon here. And that photon carried Q with it, right? And we know there are higher order diagrams, right? I could write down the electron and the muon here, and this thing, right, this photon here could generate this little loop inside of it, right? Something like this. And I could have higher order diagrams where I had, say, this exchange photon. I could have it generate 2 loops inside of this thing and go off in this way. And there's 2 ways you can think about this conceptually. One, you can think about the electrons as having fundamentally some charge, and that there are different, right, that the propagator terms in these diagrams are changing. Because what's happening here, as I go across this thing, right, I always have to have, right, I always have to have essentially enough energy in this system to generate these loops and have extra probability available to me to generate these loops here. And so you could somehow think about that my probability of generating these additional loops has to be related to the momentum transferred out of the, the electron side of these things. And right, so somehow the probability, right, we know that these diagrams relate to, right, these propagator terms relate to Q squared, and these modified propagator terms better relate, right, the probability of these diagrams relates to the Q squared on this side, and it's modified by this. Which way does it go? Well, as I go up here, I'm more likely to produce this diagram. Oh, sorry. I'm circling something on my screen that you guys don't see. I'm more likely to produce this diagram. Where? Am I more likely to produce that when I have low Q squared or high Q squared? What do you guys think?
It'd be very high, right? Where you have more energy to play with.
What else do you think? What do other people think?
I also agree.
So what is Q squared? What's another way of thinking about Q squared? Q squared's like the momentum, right? Q squared is like something like the momentum. And how does that relate, right? Like if I have a photon, think about this like a photon. If I have a photon, can I relate the momentum of that photon to a distance scale? How does that go?
Oh yeah, the wavelength.
Yeah, through the wavelength, right? So the momentum is something proportional like to the frequency, but the length scale is going to be inversely proportional to that thing. So for higher Q squareds, right, the higher momentum of that exchange photon, the smaller distance scales you're probing. And it turns out that means, right, so you do have to have enough energy to produce the pairs. But once you have enough energy, it turns out that the higher you turn up Q squared, that Q value, that momentum transfer, the smaller the distance scale that you're probing in the theory. And so you can think about this like the electrons and the muons will exchange, right? We'll have a larger momentum exchange if they, right? It essentially is like the electron and the muon in this interaction are able to get closer to one another, and they can exchange more muon over this really short range. And when they do that, they have to exchange a really high Q photon to when they're at that scales, right? So the scales, right? You can think about like the spacing between the particles is also something that dictates the amount of force momentum that gets exchanged by these two sides. Okay. And so, right, as long as these processes are kinematically allowable, it turns out this guy is favored. Oops. Did we lose my screen again?
Yeah.
Turns out this guy is favored at, right, this guy is favored at lower Q squared, lower, more likely, more probable at lower Q squared. But there's another way that we can think about this, right? We could also think about this in terms of the effective charge of the electrons. So here's what I mean. These guys are these guys are like electron, anti-electron pairs. We've talked about this several times, right? And so you can think about them like that there's some medium that these charged objects are traveling through, and that there are suddenly these little dipoles, quark or electron, anti-electron little dipoles that appear out of the vacuum, and they will see the fields from the different charges, and they have time to try to, they'll polarize themselves in the field generated by these charged particles. And when they do that, that creates a charge screening effect, right? So the electron that's cruising along up here, because there are these bubbles, right? There are these little neutral dipoles that are in the way of the electron, right? This electron up here sees all the charge below it, right? All the charged particles below it. And so it's somehow interacting in the field generated by all those charged particles. And since I have a bunch of neutral, suddenly that electron traveling on the bottom, we can say that that has some total net charge that we're going to call like the effective charge of this thing. And this effective charge here would be less than the bare charge of the electron, right? Because I have more of these little bubbles. This guy that's traveling above essentially thinks it sees a particle with less and less charge as it cruises along. Right, and so you could plot that, right? You could imagine plotting as a function of Q squared, what happens to, say, the effective alpha in QED. And we just saw that as Q squared goes down, right? As Q squared goes down, the charge of the electron is going down. Okay, so it looks something like this. This thing would go to, right? This thing would go to like alpha E, and it would go something like this. Nope, that's not right. At high Q squared, this thing better be approaching alpha E, the bare charge, and it's going to ramp up, right? As Q squared goes down, right? It's going to ramp up something like this and have an asymptotic behavior. Right? So for really high energy exchanges, alpha E, right, is sort of growing here. And for really low energy exchanges, somehow the effective charge is altered by these vacuum polarizations. And this is something you can measure. You can imagine you can measure that experimentally, right? Have low momentum transfer and try to do a measurement of what the charge, right? The charge of the two objects was that it scattered off of, what the potential had to look like, and if their charge was altered. And then you can play the same game in QCD. And we're basically out of time now, but the takeaway is that, okay, so this guy has a form. It's like alpha effective, right? Alpha is a function of Q squared, has a term that's like alpha naught, and then it's got a functional form that's like 1 plus some constants times a logarithm that's dependent on Q over the mass of the quark squared. It looks something like this. Okay, the functional form of that coupling is some logarithmic thing. What does it look like for QCD? And this is the last thing we'll say today. And then we'll say a few more words about this on Tuesday, and then we'll start on weak interactions. Well, for QCD, I have the quarks, and the bare processes, they can exchange a gluon. And so I could play the same game. I could have the quarks, and I could have a gluon, and then I could have little quark-antiquark bubbles appearing. But there's another thing that can happen in QCD. I can have the gluon, and now the gluons are allowed to self-couple, and so I can have additional gluons appear. Right? I can have gluon loops appear inside of this diagram. And these diagrams here, where I have the lepton loops appearing, do the same thing that they did when QED. They make some charge screening, and they make the object look more color neutral. It reduces the effective color of the quark as I turn up Q squared. Or sorry, as I turn down Q squared. But what about this guy? What does this do? Well, this guy actually does exactly the opposite thing here. This essentially puts more field strength between the two particles. Okay? Puts more field strength between the two particles. And so they're competing here, right? So this guy wants to increase the effective color charge of the objects, this gluon loops, and the lepton loops wants to decrease them as I'm changing Q. And when you go through the theory, what you find is that these gluon terms win out. And the effective alpha for the color charge as a function of Q squared looks something like this. It looks like the bare alpha over, and then there's essentially so 1 plus constants, and then a term that's like ln, again, Q squared over M squared, something like this. So it has the inverse behavior, okay? In this thing, if I plot alpha x as a function of Q, the effective coupling, right, decreases down to the bare the bare alpha s. Alpha s is decreasing as I crank up q squared. And this is why, so this is why colored objects, or at least this supports, right? This theory is a way to explain why colored objects aren't allowed to, right, escape their, right, their bound structure, right? Basically at small q, I'm talking about large distance scales, and what happens is I increase the distance scale, the distance between the quarks, the coupling, the effective color charge goes way up. And so that gluon field becomes stronger and stronger, and the particles can't escape one another, right? The strength, that interaction strength, they hold each other together very strongly. But at high energy, right? So there's, right? So that keeps the objects bound. At low energies, the effective charge, color charge is very huge, and the particles can't escape one another. But at high momentum transfers, alpha s goes down in a significant way. And it goes down enough that it drops below 1. And if I go to high enough energies, I can use perturbative theory to calculate QCD. So at the highest energies, I can check, I can build colliders and have really high energy interactions, probe the smallest distance scales, use perturbation theory to check QCD at that range. But that breaks down when I look at the stable objects at low q squared or large distance scales, and it forces them to be bound. Okay, we're going to stop there today. We'll mention this a little bit more next Tuesday. And we're going to start the chapters on, we're going to talk about weak interaction next Tuesday as we go along. Okay, anything else? All right, have a great day.